So today I'll be talking about radicals and rational exponents. And so just to get started, I'll go through a few of these practical applications just so you know how the concepts that I'm talking about are commonly used. So there are a lot that I list here, but just for a few, there are a lot of things that can, especially in geometry, you get a lot of exponents just because, let's say if you're working with a three-dimensional space, then you'll have to cube whatever it is that you're talking about because it's in 3 dimensions, right? So then you'll cube it. And so because of that, that can be helpful when working in objects in a 3-dimensional space. Then there's also financial mathematics with exponential growth and decay models, which involve rational exponents, such as compound interest formulas, use the concept of exponential growth. Then there are also ways in which, I guess with computer graphics, that can kind of be the same as geometry, since it's like you're creating a 3-dimensional space. In some cases when you're using computer graphics. And then there's a bunch of other ones that you can look through within my project that I shared in the math demo too. But we can just jump right into it here. So let me.
Wow, pretty slides.
Thanks. All right, radicals and rational exponents. First off, what is an exponent? So an exponent, also known as a power, is a value that indicates how many times to multiply a base number by itself. So for example, we have 4/5 or 4 to the power of 5. This 4 is the base number and the 5 is an exponent. It's basically the way you write it is just a little tiny number above the base number. And what this means is that we need to multiply 4 by itself 5 times. So 4 times 4 times 4 times 4 times 4. As you can see, this can save a lot of time if you are, multiplying something by itself a lot of times. And this also means that the number gets big really, really quickly.
That's why remember the multiplication tables is so important because so much math requires you to do multiplications quickly.
Mm-hmm. Yes, definitely. So what is a square root? A square root can kind of be thought of as the opposite of an exponent, or the inverse of an exponent. So the square root of a number is a number that, when multiplied by itself, gives the original number. So basically, what I mean by the inverse of an exponent, it's like the inverse of the exponent of 2. So for example, 4 to the power of 2 is 4 times 4, which is 16. The square root of 16 is 4 because 4 times 4 equals 16. So you're basically trying to find that original number. So if you know all of your, multiplication facts, like the example we used earlier, 7 times 7 equals 49, the square root of 49 would be 7, and so on for all your multiplication facts. The square root of 36 would be 6, the square root of 25 would be 5, and so on. So because of this, 4 times 4 equals 16, you can see how the relationship between these numbers. So what is a radical? A radical is a mathematical symbol that represents the root of a number. The most common radical is the square root, which we just saw, which represents the second root of a number. So for example, the square root of 9 is 3 because 3 times 3 equals 9. And this radical used here is how we're representing that. So there's also radical indexes. So the number outside of the radical system is called the index or root index. For a square root, the index is 2. Just like when you have a, the exponent, if you have 4 to the power of 2, it would be 16 because you're multiplying 4 times 4. The same thing is with roots. And so, for example, let's say you have the index of 3. For an exponent, sorry, for the exponent of 3, it would mean you're multiplying the base number 3 times. If you have 3 as the index of a radical, that would mean that you're getting the cube root. And so, for example, if you have a radical of the number for the radical is 8, and the index is 3, then the answer would be 2, because 2 times 2 equals 4 times 2 equals 8. So you can kind of see how that works, right?
What is an index?
So let's say we have a square root of, this is very skinny. Let me see if I can. You can see that all right, right? Okay. We have the square root of 16 equals 4. This is the same thing as if I have a little number here that says 2, because this means that 4 is multiplied by itself 2 times, right? 4 times 4 equals 16, right? And so this is because we reference 4 2 times. And so because of this, this number 2 is the index. So that's the index. Same thing if you have an index of 3, using the example I just gave, of if you have the cube root.
The index is 3.
The cube root is 3. The cube root of 8 is 2, because 2 times itself 3 times is 8. So that's what the index is referencing. As the index increases, the nature of the root changes. For example, an index of 3 means that the answer is the number when multiplied by 3 equals the original number. Okay, so for example, we have this base number of 8, the index is 3, and the answer is 2, because 2 times 2 times 2 equals 8. All right, now there is the concept of simplifying radicals. You can simplify radicals by finding perfect square factors under the radical sign. For instance, the square root of 12 can be simplified as 4 times the square root of 4 times 3, and the square root of 4 is 2, and then 3 cannot be simplified any further. So I don't know, does that make sense to you, Isla? So let's say we have the cube root of 32. And 32 isn't a perfect square root, right? The perfect square root closest to it is 6, and 6 times 6 is 36. But because of that, we don't have a perfect answer to this that's just a round integer. And so because of this, we can simplify it by thinking, what are the factors of 32 that might have a square root? One of them is 16, because 32 divided by 2 is 16, and 16 is a perfect square root. And so because of that, this is the equivalent of saying the square root of 16 times 2. And 16 does have a square root, and 2 does not. But because of this, we can further simplify it to 4 times the square root of 2. And so the square root of 32 is the equivalent expression to 4 times the square root of 2. And so, yeah, that's how you can simplify radicals that are perfect square roots or square factors. So now we have rational exponents. So rational exponents are another way to express roots. Instead of using the radical symbol, you can use fractional or rational exponents. So the radical with the index of basically n times for the index of n for whatever square you're looking for is the equivalent of an exponent of 1 over n. So for example, the square root is equivalent to an exponent of 1/2. The cube root is equivalent to an exponent of 1/3, and so on. Does that make sense? Basically, let's say we have not two. Let's say we have 8, the cube root of 8. How can we express this as an exponent? We can do that by bringing 8 up to the 3rd power, or the 1/3 power. And so this is just another way of expressing to express roots without using a radical symbol. And this is helpful if, let's say you have, if I erase this, let's say you have the cube root of 8 times 4 to the 5th power. How would you solve this problem, right? And so I'll get into that later, but essentially this is just one of the steps that will help us get to this answer. Okay, so drawings. All right. So here are some examples. The square root of x is the same thing as x to the 1/2 power. The cube root of x is the same as x to the 1/3 power. I don't know how you would say that, but the 4th root of x is the same as x to the 1/4 power. All right. So now I'm getting into properties of rational exponents. And essentially what properties means is that when you're working with these rational exponents, what are some rules that kind of define the nature of how you can work with these rational exponents when you're solving problems with them? The reason why I actually decided to make a project on radicals and rational exponents is because I find a lot of these rules to not be very intuitive. And these are just things that you kind of have to memorize. A lot of algebra I've found to be very intuitive and kind of just make sense to me in my brain, but a lot of these rules just don't. So that's why I wanted to kind of put it down and make it so that I could try to understand it better and remember it more. So the first is the product rule. So essentially this means that, let's say you have two exponents, two rational exponents, meaning that it's a fractional exponent, meaning that it's actually a root. So for example, you have x to the power of m over n times x to the power of p over n. And so these are just variables representing, whatever number that might be. And what this means is that the way you can simplify this is that this would be equivalent to x to the power of m plus p over n. So I'll give you an example. Let's say we have 8 to the power of 3 over 4 times 8 to the power of 2 over 4. I guess this could also be simplified. Let's say that could also be 1 over 2, but we're just making it so that it has the same number. Because if the denominator here is different, then this property would not apply. But if you do have the same base number and you have the same denominator, then you can do this. That also means that you can, let's say we have, if we don't have such an easy question here, and it's something like, 5 over 7, you can still make it so that these two fractions have the same denominator by finding a common common denominator, like for this, it would be 28. But let's just go with something easier. 2 over 4. This would be the equivalent of 8 to the power of 3 plus 2 over 4, which would be 5 over 4. So now we combine these two numbers into 8 to the power of 5 over 4. So that's what this product rule is saying.
Well, Sumay, this is actually the rule, product rule. What you really needed to remember is, say, x to the power, say, of a times x to the power of b is equal x to the power of a plus b. Because
Right,
here
yeah.
a is just
That's true. If the denominator is 1 for both of these, then
Yeah.
that would just be
yeah, so m
same.
plus e, right? So that's all
Right.
you need to remember, because whether it's the power is a whole number or fractions, the rule is the same.
Yeah.
It's,
Yeah, that's a good point. Thanks for bringing that up. So that would work if you have 8 to the power of 2 times 8 to the power of 5 would be 8 to the power of 7, because 2 plus 5 is 7. And the reason why this is the exact same rule is because this is the same as saying 8 to the power of 2 over 1 and 8 to the power of 5 over 1. So yeah, thanks for mentioning that. Okay. So now moving on, there is the quotient rule. And so this is pretty much the opposite. If you have an exponent divided by, an exponent, then it would be that minus that other exponent. So it would be the exact same concept. If you have like 5 to the power of 4 divided by 5 to the power of 2, it would equal 5 to the power of 2, because 4 minus 2 equals 2. Does that make sense? It's basically the opposite. Okay. All right, so that's just 2 of the properties, but we can keep going. Next is the power rule.
So do you need to memorize all these rules?
If you are working with exponents and you're doing these sorts of problems, then if you get the rules wrong, then you'll get the answer wrong.
Just like with formulas.
Yeah, so it is something that is helpful.
I think Sumay is showing the rules in a more complicated way with fractions, but really, it's the rule. The simpler version of the rule is that you can just have the whole numbers there.
Yeah, I'm gonna be using whole numbers as examples because I think I overcomplicated it here.
Very complicated, but
yeah,
the rules actually are simpler than what Sumay is showing here.
Yeah,
she's showing a complicated version.
I think I should probably update it with the whole numbers. But yeah, so
and then you say just the same rule applies if the numbers are fractions, right?
Yeah. So the next one is the power rule, which means obviously power exponent. This is when you're raising an exponent to an exponent. So that's, for example, let's say we have 9 to the power of 3, and then you take this and raise it to the power of 5. This would be the equivalent of 9 to the power of 3 times 5. Sorry, that's to the power of 3 times 5, which is the equivalent of 9 to the power of 15.
Oh, I thought you just meant the numbers keep getting smaller and smaller and smaller, but you do the parentheses.
You notice it's different. So if this is 9 to the power of 3 times 9 to the power of 5, then you get 9 to the power of 3 plus 5, right?
Right.
So you want to
Yeah.
write out these two so you can see the difference.
Right.
When it becomes the these are so
3
really
plus 5. So this is, Isla, this is why it's important, is because let's say you have 9 to the power of 3 times 9 to the power of 5. That would be 9 to the power of 8. But if you have 9 to the power of 3 raised to the power of 5, then it would be 15. So these are two completely different numbers, and especially since we're working with exponents, this number is way bigger than this number. Yeah,
this is
so
what you need to know really is the difference, right? When you are adding the numbers or times the numbers.
Yes, definitely. Okay, so then the next is negative exponents. And this is basically how can you represent negative exponents other than just saying that this is a negative exponent. And the way you can do it is, let's say you have 7 to the power of negative 4. This is the exact same as 1 over 7 to the power of 4. And so this can help you when solving problems, and in some cases. So
1 over 7 or 7 over 1?
1 over 7. Because here's the thing, with negative exponents, you're basically having this number get exponentially smaller instead of exponentially bigger. And because of this, if you have 1 divided by 7 over 4, 7 over 4, as you continue to multiply 7, this denominator gets bigger and bigger and bigger, meaning that this actual number gets smaller and smaller and smaller, right?
Oh.
So that's why this makes sense. Yeah, so those are just 4 properties of rational exponents that I mentioned in this project. I mentioned all these practical applications in these slides as well. But those are the basics of radicals and rational exponents.
And we talk a lot about compounding, right? And that's really is exponent.
Yeah.
When you invest your money, if it's growing at a certain rate, every year it's going to compound your return. So that's when you use the exponent to calculate your returns. And also when you use the opposite is say, okay, if you have a goal,
exponential decay.
Yeah, if you want to say in 10 years you want to grow your money, double your money, then you want to figure out what kind of return you need to get in order to compound it, double your return in 10 years. So it's used in finance all the time, like investing. Just
Yep. Thank you for your thoughts,
also
Mom.
like it's applied as either you were calculating an area, right, of a shape, right? If you think about if it's a square, it's really to the power of 2. And if you needed to figure out the side of a square, then you needed to take the square root of the area. If you know the area, then you take the square root, you get the length of the side.
Yeah, you take the square root.
Yes. So that's also is useful for thinking about areas. And to the power of 3 is that if you are calculating, say if it's a cube, right, what's the size of a cube dimension, right? When you calculate an area, it's the power of 2. But if you are calculating the size of a cube, 3 dimensions, it's to the power of 3.
Mhm.
Oh. Okay.
Because you're just multiplying, just like let's say you're calculating the area of a square, and the
Mhm.
square obviously has equal sides. Let's say it's 4, then you would be multiplying 4 by 4, which is the same as 4 squared, right?
Mhm.
And then let's say you have a cube instead, then you would need to
4 times
multiply
4
that
times.
again, right?
Right.
And so that would just be 4
That's why it's
cubed.
called cube and squared.
Exactly. There you go.
That's easy.
Yeah.
Right.
So awesome. Well,
Mommy,
this
do
was
you have a
fun.
project?
Oh, I wrote a project, but I presented it at the adult demo day, but it's about the gradient descendant.
Well, I also will want to put these up. I know, Isla, you also have focus friends in 20 minutes, so you might want to take
Yeah.
a little Zoom
Right.
break.
Yeah.
I'll do another project and then I'll present at the
I
math
would
demo.
love for you to present on the math demo day next week.
Yeah.
All
That
right.
would be
Did
so
you
fun.
know my mom had the best test scores in all of China?
Yep, the very best.
No, she was in 10th
You were
place.
10th in the
Right.
whole country. Well, you were 10th place in the province, but you were the highest ranked province, and probably 10th place in the whole country.
Yeah.
Too.
But she was in 2nd place in the practice test, but the only reason why she didn't get a better score was because she stayed up. It was because
I didn't sleep
of nerves. Yeah.
Okay.
So
well,
yeah, my mom's an expert. So what's
this is
next
very
one?
fun. Yeah. All right.
It's awesome.
Bye-bye.
Bye.